see, basically Terrier is an armoured battlefield JCB. So for the agenda for this morning then, we're going to look at the support scenario for Terrier. I'm going to be giving you lots of definitions because I understand some of you will be new to the defence industry. That'll lead us on to talk about the objectives from the modelling activity. Then I'm going to talk about data management within the suite, the human-machine interface, and there are actually 15 different outputs that come from the suite, but we'll just sort of look through some of the key ones and skip through some others. I'm certainly not going to talk in depth about all 15. And then we'll wrap up with some conclusions and some sort of summary. So this is basically the support scenario. We've got a fleet of vehicles that may be operated anywhere within about 4 operating theatres, 2 of which are training, 2 of which are operational. If there's a failure to the equipment, then an item, well, the failed item will obviously be removed from the vehicle. Generally speaking, it's not cost effective to return the item to industry for repair, which is obviously shown up here. So that would be the item would be discarded locally. However, there is quite a significant percentage where it is economic to return the item for repair. So that would come up the supply chain to the central store and to the supply base. In the baseline scenario, spares are only held at the central store, and there are different transport times between the theatres and the central store, which obviously need to be taken into account. So, no, sorry, I've got a button here. Demands from each of the theatres have different high priority, and quite clearly the demands from the operational theatres are given highest priority. There are 60 vehicles within the fleet, and they can be moved around to any of the theatres. Each theatre has a different usage profile, and the usage profiles vary with time. There's a contractually agreed baseline fleet usage level. Each vehicle is modelled as an assembly of 900 different part numbers, and each of those part numbers may have a different quantity fitted per vehicle and a mean time between failure, for example. And of course there are other parameters which are unique, such as a scrap rate for each item, the supply, resupply and repair times, and cost to reorder and to repair, obviously for the repairable items. And finally for this slide, there's an agreed initial stock at the central store location. So to start with some definitions, we saw in the previous slide that all demands are coming up through the central store to be satisfied at the central store. And when a spare is available in the central store to send out to theatre, then we talk about that demand having been satisfied immediately. And we, as I say, we talk about demand satisfaction. If demand comes through and there's no spare available to satisfy that demand immediately, then that item goes on back order. Something we call demand satisfaction rate, which is key to the key performance indicators that we're going to measure, and this is defined as the quantity of demands that are satisfied immediately divided by the total quantity of demands, which is quite clearly a ratio. We talk about line items, and for example, you'll have seen in the video that the wheels are clamped together with a mechanism that includes some nuts. So each vehicle has several dozen of these nuts in them. And whilst there are several dozen part nuts, that's just a single line item. So that's referred to as a line item. There's a term we use called consumables, and these are the items that it's just not worth sending back through the supply chain for repair. So they are consumed. And within the Terrier model, we've got about 800 consumable items. And then we have repairables, of which there are approximately 100 line items. And these are the items which are sent back to industry for repair. We're very shortly going to talk about the analysis requirements, but I've got even more definitions to give you before we get there. The primary key performance indicator was this demand satisfaction rate. And the requirement there was to have an 85% demand satisfaction rate within a time period that was determined by blocks of 3 months. And we had to have a minimum number of 40 demands within each time period. So to illustrate that, if we had a block of 3 months with 38 demands in, then that's not achieving the 40 demands minimum. So we then, if we've got the subsequent block, which has got 2 or more demands in, then we've got a reporting period there, because we've got more than 40 demands, and that reporting period is 6 months. And we would have separate reports for repairables and consumables, so quite clearly we might have some months where there's no reporting periods for say, repairables, because we've got a relatively low demand rate. A secondary KPI was this demand satisfaction time, which we wanted to be less than 90 days. A demand satisfaction rate is all very, very well for measuring when stock is available, but it ignores, in this case, the 15% of occasions when there is nothing available. And arguably a demand satisfaction rate of 80% with a resupply time when there is shortage of 2 days might be far more attractive than a demand satisfaction rate of 90% with a resupply time when there is shortage of, say, 2 years. So that demand satisfaction time is quite important. So those are the 2 KPIs, and what we wanted then from the modelling effort was to predict the performance against these KPIs with the agreed spares that we had in the central store against the baseline usage that we had. We then wanted to analyse the effect of having these spares at 3 additional levels above the baseline level of usage to get some feel for that performance. And then something which became known as Objective 2 was to determine the additional spares that would be required for these additional 3 levels of usage. And of course, if we got more spares, then we got higher costs associated with that, so we wanted to know about that as well. Not a contractual consideration, but also important, was the reputation of BAE Systems. It was quite possible to meet the KPIs with flying colours, because we're talking very much about, with DSRs, we're talking about effectively average performance, yet still fail as far as perhaps supplying power packs is concerned. Power pack being the driving unit for the vehicle, predominantly the engine and the transmission unit. So the consequences of failure to meet KPIs, the contract included a gain share arrangement, and this was predominantly there to encourage BAE Systems to improve processes. And there was a sliding scale of payments by the MOD to BAE Systems. And failure to meet the KPI meant, within a particular reporting period, meant loss of gain share, which of course meant loss of revenue to a commercial organisation, which is a bad thing. So it was necessary then to make predictions with a high degree of confidence. Right, more definitions then. I'm going to go through a sequence of 4 slides now, which explains why we want to have many replications within the modelling suite. So first of all, I want to define a percentile. And what we've got here is a normal distribution. Oh, there it is. A mean value of 10, standard deviation of 1.5. And here we have a value of x across the x-axis, and on the y-axis we have the probability from the distribution that the DEX will take any one of these figures. Now, I'm going to show this in cumulative form, and those of you familiar with these charts will appreciate that actually the red line should always be above the blue line, but because of the crude way I've created this in Excel, that's not actually come about. But for the purposes of this presentation, we don't need to worry about that. Here we show the 50% probability that x will take the value of 10 or less, which is the mean or less. And when you've got a symmetric distribution, you've always got a 50% probability that the value will be the mean value or lower. And here we have the 90th percentile, or the 90% probability of the value that we're going to get from this distribution. And in this particular case, the value is approximately 12. So the requirements for many replications. What do we mean by statistical confidence? There's a couple of slides on this. Within this, I'm going to talk about different populations of data. And we're going to start off with a fairly easy one, which is the population of all throws of a fair six-sided die. And here is some information about that. We know, for example, there are only 6 outcomes. If it is a fair die, then the probability of each outcome is 1/6, which is shown as a decimal there. If we then accumulate those probabilities, we end up with 1, which tells us that we've considered all possibilities. What we've now got excuse me, are some samples from the population. And here, obviously, we're just looking at a subset of all the die throws within each sample. Here we'll look at some dummy data from one sample of 1,200 throws. And here we have the quantity of outcomes, of each of these outcomes, obviously the quantity of 1,200 throws, to generate the probability from this sample of any one of these outcomes. We just divide the score by the total quantity to give a probability. And then again, we add these up to get the cumulative probability. We've got 1, so we've accounted for all occurrences. Something we could do with this sample is to calculate a mean value. So we've done this by multiplying the outcome by the probability to give a figure. And by adding these up, we see that we've got a mean value of slightly over 3.5. Now we actually know from the expected probabilities that the mean value for the population is exactly 3.5. So quite clearly that this sample isn't entirely representative of the population, but it's not far off as far as the parameter of the mean is concerned. I want now to show, to the next stage, show you some diagrams with the view of this discrete uniform distribution isn't going to be so visually useful, so I'm going to move on to talk about samples from a different population. We're going to look at a sample mean of 14. We're assuming here that the population that this sample is being drawn from has a normal distribution with a standard deviation of 1.5, and we have a requirement to work out with a 95% confidence what the population mean is that this sample has been drawn from. And we basically do that by having identified the sample mean. Whilst the process I'm going to talk through is done graphically, obviously in practice you would do this mathematically. But because, and I'll explain why shortly, but because we want a 95% confidence limit, we work out where in this case the lower confidence limit curve is, such that the area under the curve to the left of the sample mean is 97.5% of that distribution. And similarly for the upper confidence limit curve, we want the area to the right of the sample mean to be 97.5% of that distribution. And that gives us then a 95% confidence interval that the population mean will fall between 11 and 17%. And quite clearly we've got 2.5% this way, 2.5% that way, which is why we end up with a 95% in the middle there. We'll now look at yet another set of samples. This time we've got 95% confidence intervals with samples of size 7 from a normally distributed population with a mean of 100 and a standard deviation of 10. And you'll see here that we've got, I should say that I've pinched this off Tinternet, and so I've given a reference to that. We see here that we've got one of the samples where the confidence interval excludes the population mean, and in this example that we're talking about, we're basically saying that 95% of the confidence intervals will contain the population mean, or more generically, the confidence limit percentage of confidence intervals will contain the population parameter that we're measuring. Right, so requirement for many replications. With the Terrier project, we're interested in the confidence intervals bounded on a single side, rather than on the double side. On the double side, we were looking at two sets of distributions, but here we're just looking at the single side because we're only interested in this 95% confidence of the demand satisfaction rate being greater than or equal to 85%. So again, another set of data. This time we've got 144 samples of 1,200 die throws, and compare that with 1,728 samples of 1,200 die throws, and we see that whilst the expected probability of throwing one is obviously 1/6, as we've increased the quantity of samples, we've tended to get closer to that value. And indeed, if we look at the 90th percentile, we'll see that this value is also coming down, which again suggests that we've got more accuracy. So the message here is that when we're doing this sort of work, we want to do some sort of statistical analysis on the output. We do need a lot of replications. However, it's not always as simple as that, and it can be quite tricky to actually interpret the results from many replications. So with the help of Lana, Persides have generated this document. Our reference number is PER 1928, which explains the potential pitfalls and provides guidelines on how to handle them. And if you want a copy, then we can almost certainly make that available to you. Right, data management. The suite, as we saw earlier on, is driven by witness. Fundamentally, we have 3 different Excel worksheets that provide data into there, and then we generate results, analyse the results, and produce some outputs down here. This is controlled by a witness configuration language file that controls, as I say, at the moment, 144 replications. And each time, that command language file is just a simple text file with obviously specific terminology in it, which witness can interpret. So you open witness up, you say open the witness command language file, and then control is given to the command language file. So on each iteration, when witness is opened up, data is imported from these 3 worksheets. So there's usage data, which describes the usage by theatre over time. There's item data here, which is things like the quantity of items fitted per vehicle, the MTBF for each item. And then we have another thing here called supply repair. I'm going to have to take another drink. All the KPIs that we mentioned were all measured at the central store, but quite clearly the ability of the supply base to supply serviceable spare parts to that central store impacts upon KPI performance. BAE Systems were particularly keen to ensure that the power pack repair agent had sufficient stock, so we introduced this facility to model supply repair. And basically, as a result of that activity, that modelling activity, BAE Systems ended up procuring more gearboxes and more engines to give to the repair agent to improve the stock holding in the central store. So each iteration then, data is imported into Excel. Results are then exported for each iteration into an Access database, and that is very much just a back-end database for the data. Depending on, particularly on the usage that we model, this database would have demand historical histories for between 1.3 and 2 million demands, which we're then going to be analysing within the Access. Now, this Access here is just a front-end container for a few forms and quite a bit of Visual Basic VBA code, Visual Basic for Applications code. And this is crunching the data in here and producing output that we can then feed into 15 different spreadsheets. Now, what this is doing is very much using horses for courses as far as product is concerned, because the data acquirers are comfortable in Excel, clearly the event-based simulation tool, very much for the reasons that Nathan mentioned earlier on, is the right product for this analysis. And then for the data handling and the data crunching, we're using Access down here. And then finally, for presentation of information to the decision makers, they again are going to be happy with looking at Microsoft Excel. That wasn't supposed to start. I probably can't stop that now. Oh, where's the hell? There we go. This is the witness model. It's not in the form that we saw the scenario diagram earlier on with the theatres and the central store and the repair agent. It's more in a flow process. I'll quickly describe what's going on, and then we'll have a look at it, and I'll talk through a more interesting part of this side of it. This is obviously useful for building the core of the suite, but and again the same with Nathan. Once we were happy, having checked that things were doing what we expected them to do within here, we then just run this in batch mode, because fundamentally what we're trying to do is to populate our database with data for analysis. So at the beginning of each simulation, this store here, this represents the central store. This is populated with the spare parts that have been agreed should be held. Then each day there's an object comes through to represent a day, and on its creation we determine what items have been demanded, what theatre has demanded them, and that then results in demands being created here for each of those. Then we get to another machine which sends the original demands down to a theatre pool for demands, creates or duplicates the demand for here, so that this represents a demand being placed on industry to resupply. Sorry, I've jumped ahead of myself. We duplicate the demand to the central store, so that the stock there is passed through to the theatre stores, so there's something here to satisfy the demand that came down here. And then if the item that's been demanded is a consumable, we place a demand on industry to resupply the central store. If the item is repairable, then it spends time coming back through the repair loop to be assessed by industry. If it's a power pack, it comes through the supply repair loop. We then end up with repairables and consumables, for that matter, being entered back into the central store here. We have the capability for each theatre, and a lot of this, as we'll talk about later, a lot of this is actually user input driven rather than being hard coded. We have the facility to transfer stock from here to be held on a semi-permanent basis by the theatre stores. And you'll see shortly when I run this that we'll get a lot of demands that appear here and stock moving around to populate these. And then we have a facility to put demands in at this level to drain the stock from here to return it back to the central store. So now I'll try and run that. Oh, there we go. So we've got items, here we go. Here we've got the demands coming in then to populate the first of these theatres. Here we've got the items in transit getting from the central store to theatre. We've now got a month later, we've got additional demands to move stock from here to the second theatre of operations. You'll see that the training activity is still happening. We've still got a queue of repairables being returned to industry for repair. We've now got the first set of stock arriving in that first operational theatre. And a month later, there we go, we've got the additional stock arriving. Shortly we'll start to see demands appear here in the operational theatres. I'll let that catch up. There we go, some demands in the first operational theatre, and you'll see that this queue has now increased because we're now obviously increasing the number of failures that are going on because we're using the vehicle more. We've now got demands coming in for the second theatre of operations. You'll also see that this queue has increased because obviously we've got more demands coming through this system down to be satisfied with by spare parts for the system here. Shortly, there we go, we've now got demands that have come into Theatre 1 to return stock from here to there, and shortly we'll see a similar activity there for Operational Theatre 2. Moving swiftly on, we'll now talk about the human-machine interface. And this is basically what the front end of the second access database looks like. Oh, again, I didn't mean that to happen, apologies. We've got 15 different outputs. We've got those associated with demand satisfaction rate and stock out risk here, cost related outputs here, and then supply chain related outputs there. And the next animation shows what happens when we click on any one of those buttons and we get a different group of what we called report subset options that come up. The full set of report subset options are here. I'm not going to go through them all, but just to give you a flavour, we can time slice the results that we're getting by specifying months from and months to. Here we show here for the maximum demand satisfaction rate period our primary key performance indicator, the minimum quantity of months in a block, the minimum quantity of demands in a period, and the target demand satisfaction rate. And as I said earlier on, we could easily have hard-coded that in, but it wasn't really a lot more work to produce this front end, so that we've now got a product with much greater utility because we can tailor the content of the reports. If we press this FRP product button, then quite a useful modelling, this illustrates quite a useful modelling technique, whereby this has all been data driven, so this has been read from the Excel input usage file, and we've assigned a prime number to each of those, and obviously that assignment has been done in code in the VBA. Then when we select any of these, the product of this prime number is shown here, and that product can then be sent through to the VBA and decoded, and that's a far easier way, much tidier way to let the code know what choices we have made here. Right, the first of the outputs, and this was output 1, this was the primary key performance indicator. It's subsequently changed, but there's a useful point to be made with this in the next slide. The key performance indicator at this time was that we wanted a demand satisfaction rate during year 4, which was when we anticipated having those operations, to be greater than 95%. Now, some may think that actually what you want is 100% confidence of 100% demand satisfaction rate. But of course that would require, in theory, an infinite quantity of spares, which is going to be somewhat expensive, as well as requiring a lot of storage space. So in practice, here's our target DSR and the target confidence rate. Rather than being in that corner of that quadrant, we want to be close to that corner of that quadrant. And with this dummy data set, we've got pretty close. So and what that has showed us is that within the support year 4, we've achieved this KPI. However, if we look at the median demand satisfaction rate, this time by month, we see that within year 4, as per the previous slide, we achieved the KPI. However, in month 49, we drop below that target demand satisfaction rate. The system is still recovering from that relatively intense use of the 2 operations. So whilst we've met the KPI, we're now running the risk of reputational damage within month 49. So we want now a facility to drill down into the data to find out what we can do about it. So output 3 looks at the stock out risk. So here we've got the maximum stock out risk with 90% confidence. And we're showing 3 items So in month 49, we're saying we've got 100% confidence, sorry, we've got 90% confidence that 100% of the time we're not going to have, or the maximum stock at risk we're going to have is 100%. So basically we're expecting never to be able to satisfy demands for those spares within that month 49. And then, of course, there's the other item where sometimes we will and sometimes we won't. So those are the items where we might wish to consider increasing the stock holding to improve performance. This then is the actual primary KPI that we're now working with. And what we're showing here is for 10, 50 and 90% confidence the maximum demand satisfaction rate that we expect to get. And this purple one here shows the confidence of achieving that demand satisfaction rate. Once again, this is all dummy data, and you'll see here that we've got different durations for the reporting periods, 21 months, 15 months, and what have you. And the code obviously just works all that out for us as we're going along. Right, the next set of outputs I want to skip through quite quickly. I don't see there's much point in talking about them in detail, but just to give you a feel for the other value that has been added by this analysis work. What we've got here is a slide that shows, again, by confidence, the quantity of what are called requirements that BAE System will place on their suppliers. A requirement is like an order for a part, but with the repairable items, there's one requirement per item that requires repair. With the consumable items, there are potentially, well, there's always one part number per requirement, but each requirement could be for a quantity greater than one. So the supply chain manager wanted to know what the sort of traffic was going to be of the requirements placed on the suppliers, so he could make sure he was going to be staffed up enough to handle them. Here we're looking at output 10, which is the confidence of when theatre spares will be issued. And you'll see that actually we've got a pretty high confidence that we're going to meet all of those within, say, 4 months. What we're measuring here is the time when the last spare that was demanded as part of that pushing spares forward to theatres, when the last of those demands was actually met. Here we've got some dummy data which talks about the long demand satisfaction times. We've got 10% confidence that we'll always meet, there's no red in here, so we've got 10% confidence that we'll always meet that 90-day target. We've got 50% confidence that there'll be a few items that stretch out for quite a bit longer than 90 days. And 90% confidence that actually there'll be quite a few more items stretching out for really what is quite a long time. So again, that's sort of another use that we've made from this. And I hope you'll appreciate that we haven't actually done any more modelling in Witness to get this data. It's just analysing the same sort of output data for different factors. And finally, this was the graph that persuaded people that we needed to buy more transmission units and more engines. And what we're measuring here is the quantity of power pack repairs that have been delayed for want of a spare. So we've got 10% confidence that there'll be no delays, 50% confidence that there'll be one delay for each of these months, and 90% confidence that what I should be saying is 50% confidence there'll be no more than one delay, 90% confidence that there'll be no more than 2 delays here and 1 delay along here. Right, this objective 2 was to determine the spares required to achieve the KPIs when the fleet usage was increased by those 3 tiers. And the process that we use for that is, having identified the baseline performance, we need to establish whether the KPIs have been met. If not, we need to identify those line items which are causing us the issues, manually increase the stock holding, reconduct the analysis with the new stock, and then we just end up in a loop until we've identified additional spares required, and hence the cost of those spares. So in conclusion then, the value added, we've assessed the MOD KPIs, We've assessed the BAE Systems commercial risks and concerns. We've got a reasonably good feeling that the spares scale that we had originally specified is going to be adequate for the baseline usage. We've provided 15 outputs in these 3 categories of demand satisfaction rates and stock out risk, cost and supply chain parameters. And we've showed the impact on the KPI values of the higher usage. We've also identified the additional stock that would be required to achieve the baseline KPI values by adding more spares to account for the increase in usage. And we've identified the additional stock required to improve the efficiency of the power pack repair agent. And then finally, something else that hopefully some of you got is an understanding now of statistical confidence. At this point, are there any questions?